This morning is Mike Cullen from the Met Office, who's going to talk to us about asymptotic solutions, asymptotic limit solutions, and this kind of leads into a discussion session tomorrow afternoon. So I think Mike's going to keep notes on points that come up during the talk this morning that can be discussed in more detail tomorrow. Thanks, Mike.
So the idea, I gave a sort of short version of this material 2 weeks ago at the workshop. That was just some highlights without all that much explanation. So the idea this morning is to do the explanation much more thoroughly so you can see how this works. But I've got the sense that people weren't quite used to thinking like this, and though it's not particularly revolutionary or difficult, it's just a bit different. So I'm going to essentially use this morning's talk to try to explain it properly. The examples will be a little bit of overlap with 2 weeks ago, but not that much. And tabled a discussion session for tomorrow, so I hope there's going to be some prolonged interruptions, which I will then write down and say, well, we'll debate that tomorrow, rather than sort of try and get through the talk now and see if that works. I should be very disappointed if there aren't some prolonged interruptions that don't have to be sort of shelved and moved to tomorrow, otherwise, so we have lots to talk about tomorrow, but we'll see how it goes. Abid, who's here, and Bob have been very good at feeding me lots of last-minute results, which is one of the reasons this talk keeps changing. And if I give this talk again in a week's time, you'll probably find there were more new results from Abid and Bob, so thank you to them. Background to this is that, as we sort of heard in Max's talk yesterday, we all believe that the atmosphere and the ocean are governed by the compressible Navier-Stokes equations, maybe not really compressible in the case of the ocean, and various other things, the laws of thermodynamics and other things. And there's nothing particularly non-computable about those if you've got a big enough computer, because when you do direct numerical simulations of very small scale bits of flows, you get the same answer as a laboratory experiment. But the trouble is that if you're trying to solve the whole of the atmosphere at once, the solution's just too complicated to compute. And if you work it out, you would solve these equations accurately, you'd need a computer 30 orders of magnitude faster than we've got now. And then though you say, well, you have 30 orders of magnitude more processors, then you start thinking of the power supply that would take, and you start thinking, well, perhaps if you could, you probably need the sun to power it, something totally stupid like that. So maybe in 100 years' time there will be such massive breakthroughs you'll be able to do this, but for the time being we have to assume these solutions are not computable, though the only reason they're not computable is they're just too complicated. There's nothing sort of especially horrible about the equations. And that means that when you're validating numerical models, the question is, well, what are you really validating? There's no way you're getting the right answer, so what are you getting? And here you start saying, well, we've known for a long time numerical weather prediction is quite successful because it can predict the evolution of weather systems, and we know weather systems in the extratropics are essentially geostrophic. So you start thinking, well, can you get these sort of flows right? And then, well, of course, the solution of the governing equation is not exactly geostrophic. So what do you mean by saying get these solutions right, or be good at computing these solutions? You hear a lot of hand waving saying we need to be good at geostrophic flow, but what do you really mean by that? Now, what mathematicians come in on this by saying, well, you can describe solutions for geostrophic flow as asymptotic limits of the full Navier-Stokes equations. And once you've defined what this mathematically, you can then use this to validate your numerical model, because you have a computable asymptotic limit, and then you can see if your numerical model reproduces that to the correct accuracy. And so now you can be precise about statements like we're good at geostrophic flow. If you hear 2 weeks ago for the workshop, John Thewburn started it off by talking a lot about mimetic properties of numerical methods. And the question is, well, do you really need these or not? Because we saw in his talk and other talks 2 weeks ago that sometimes these mimetic properties are very hard to enforce in the sort of grids you might want to use, and they push you towards a particular type of grid that might, say, have disadvantages in accuracy. So how important are these properties? And then you really need to say, well, why are these properties actually important? And they could be that they're what you have to get right to get these limit solutions right, or it could be they don't really matter. And if they don't really matter, then you don't get too worried about having to give them up in order to, say, use a particular type of grid that's more efficient. So the idea is just to be able to answer the discuss these questions in a rather more precise way and distinguish things that matter from things that don't matter, hopefully. The two obvious examples of this are, and not the only examples, are the issue of soundproof solutions, and because I think everybody thinks in the atmosphere and the ocean the flow speed is a lot less than the speed of sound, so you shouldn't really need to predict sound waves. And balanced solutions, which is where you're thinking of essentially geostrophic flows. Well, you might try and think of something wider than that under that heading, but those are the two obvious areas. There are other areas as well, I'll talk about one of them. And something that really hasn't been addressed very much by the mathematicians or the geophysical fluid dynamics people is to create such solutions where there's physical forcing present. Now, quite a few attempts, but that really hasn't got very far. Obviously, I think there's a big need to do a lot more of that, because a lot of the interesting cases, particularly in the tropics, the physical forcing is the big term, or one of the big terms in the system, and you're really looking for asymptotic limits which have the physical forcing built into them. Right, so the method, so the way you go about it is you go back to, you start off with a sort of traditional scale analysis meteorologists and oceanographers have always used, but you identify small parameters such as, well, the Rossby number, or the Froude number, or the Mach number, the Reynolds number, aspect ratio, ratio of scale to the Earth's radius. So the whole, there's a lot of parameters, and in the past there's been a tendency to try to collapse all the meteorology onto one small parameter, epsilon, but see from that that's not really a very sensible thing to do. Rupert Klein, who was here last week, I wasn't here, is an expert on sort of distinguished limits of governing equations, which means that you might require several of these parameters to tend to zero in a particular ratio. That's what a distinguished limit is. He may well have talked about that last week. And the other piece of discipline about this is you've got to some of the small parameters are usually very much smaller than others. I mean, the Mach number will usually be very much smaller than the Rossby number, and you need to take the smallest parameter to zero first before you take others to zero, or you can get some very strange results. The other point is that now we have numerical models in much higher resolution. We're interested in convective scale modelling and local modelling. We can now compute a much wider range of regimes than we used to, say, 20 years ago. So we may want to consider quite a lot of different regimes. So the method is, first of all, you do the standard scale analysis that's been done for years and years in the subject, and you derive sets of limit equations. And now, but the thing that geophysicists tend not to think about very much is to prove that these equations can be solved. So, for instance, there's been a whole industry in writing down balance equations which are accurate to exponential degree, or any polynomial order of accuracy you can think of. The question is, can these incredibly complicated equations actually be solved for more than an extremely short time interval, if any time at all? And in order to prove that, well, first of all, proving this is very difficult. It typically requires your limit equations to have conservation properties, because all the existence proofs are essentially built around conservation properties. You have to have some means of controlling the solution to stop it blowing up. And that may mean that you have to include some higher order terms. So if you just rigorously go through an expansion epsilon, some epsilon, and throw away all terms above epsilon or above epsilon squared, you may get something that doesn't have any conservation properties, but you're allowed to put in higher order terms in order to retain conservation. And that's sort of, people learned that lesson a long time ago, but sometimes it gets forgotten about. Having done that, you then have to prove that there's a solution of Navier-Stokes or Euler which converge to the limit solution at the expected rate. And that is also very hard. And if you can't do that, then essentially your scale analysis is unsustainable when you integrate in time. So you might say, well, a high order balance model is, say, 6th order accurate or something, but you wouldn't ever expect to see that 6th order accuracy in a numerical solution of the two systems, because that accuracy may not be sustainable in the time integration. So it's essentially proving that your a priori estimate of the scaling can also be achieved in an a posteriori estimate, and that means your scaling is consistent and maintainable and can be used to validate a numerical solution. can't do that, you wouldn't expect, you shouldn't be using that to test a numerical model, because the numerical model shouldn't behave, behave like that. This is obviously where a little bit of judgment comes in, because if, strictly speaking, you should only use a case where there is actually a rigorous proof published in the mathematical literature, so you know it's right. However, there's lots of results that people think are true, but they're not quite clever enough to prove them yet. And but there's lots of other cases where there's strong indication that results are not true. So, being practical, I would always tend to also use cases where I was confident the result was true, even if it hadn't actually been proved rigorously and published. I saw from the talk, yesterday, that Navier-Stokes in different non-linear versions of viscosity for Navier-Stokes seem to be much better sewn up. In other words, proofs have been achieved for right up to the optimal case. But in terms of reduced equations, I think there's a huge amount of mathematicians still to prove that's probably true. They just haven't managed it yet. So then the way we apply this is we test the convergence of a numerical method. Obviously, we want numerical methods for the full Navier-Stokes equations, because that's what we want to use in the operational models. We don't want to restrict the models to particular regimes. And what we want to do is to make sure they get the important regimes right. So we test that the numerical solution will converge to numerical solution of limit equations at the required rate. And that is a very practical way of testing a numerical method. So, for instance, it converges to a geostrophic solution at the required rate. It doesn't have to be exactly geostrophic, but it does have to be sufficiently geostrophic. Essentially two ways of doing that. In some cases you can just fiddle your algorithm for Navier-Stokes to solve the limit equations, essentially using the same discretization. You need to keep the discretization the same, because otherwise differences in the discretization are really going to get in the way, and you're not going to get the convergence you want, because you've used two different numerical methods. So in some cases you can just tweak the discretization and achieve convergence that way. Other cases it may be more, well, it's certainly easier and probably more useful to compute diagnostics. Say you might compute geostrophic departure or something like that. See an example like that. And the other thing is, the theorems are always said there is a solution of Navier-Stokes or Euler which converges to the limit solution at the required rate. And so the initialization is is very important. So you've got to start somewhere sensible with your Navier-Stokes model. If you don't get that right, or don't get that optimal, you probably won't get the required convergence rate either. But that's an issue with initialization, not modeling. So it's not quite trivial to do these tests, but you should get some useful information out.
In principle, the initial state should be the solution to the system of the equation.
Well,
So it is a circular problem.
Except remember you're solving two different PDEs. One is the reduced set and one is the full set. And you know the solutions are only going to be identical in a very trivial case. You're dealing with a case where they shouldn't be identical. So you've got to start off. So if you think they should be within order epsilon squared, you've got to start the full equations in a suitable place. So you would typically do as good initialization as you could, and then measure the difference, and then let the epsilon tend to 0 and do the same thing again. Right, now in terms of what's actually been proved rather than guessed, now the only theory, I'm happy to have some interruption if people know results I don't know. The only complete theory I know is the Bourgeois and Beal proof, who proved existence of smooth solutions to QG for arbitrary long times and convergence of Euler's QG at the expected rate. So essentially that problem is completely solved and could be used to test things. Also, for a long time, existence of smooth solutions to the Euler has known, and convergence of shallow water to the Euler has been proved. But as far as I know, it's not the quantitative result hasn't been proved. In other words, the scale analysis says that convergence should be order Froude number squared, and I'm not aware of any proof that that rate that rate has been proved. In the case of semi-geostrophic theory, the existence of weak semi-geostrophic solutions has been proved for constant rotation. Weak is quite important in this case because you want frontal solutions, so you actually want weak solutions, not smooth solutions. However, convergence has not been proved for the optimal rate, and convergence so far only been proved for smooth solutions. So there's quite a bit more work for the mathematicians to do there. The optimal rate will be all Rossby number squared in the sort of best regime to use SG. And only all the Rossby number has been proved. And for that result to be useful, it does have to be extended to weak solutions. So there's quite a bit of work there. But you test what's been done so far. Now, if you consider, say, higher order models, so if you take nonlinear balance, for instance, which is under scale analysis, that's accurate for all the Rossby number squared or all the Froude number squared, so it covers both low Rossby and low Froude regimes. There are very strong indications that the solutions of those equations blow up. In other words, you can't solve them for large times. But there are ways of regularizing systems like that. So now the issue then is how accurate is you now have to use the regularized model instead of the original model. The question is how accurate is that, and that's no one has really got to grips with studying that issue. So at the moment, it's probably not a very good idea to try to use that sort of model as your reference. So we go through the process for just looking at the anelastic limits of the 3D ordinary equations, and this is particularly related to the design of the endgame algorithm. So I don't know if there's no one from DRs here, are they? So hopefully I won't misrepresent them. So we're trying to solve the three-dimensional compressible ordinary equations, so I've just written them down in standard notation. Happy with that bit. And the interest in sound-proof solutions is the experience that you're not really interested in computing sound waves. And there are two ways of eliminating sound waves. You can eliminate vertically propagating sound waves by the hydrostatic approximation, and in terms of asymptotic limits, that's a limit as nt to the minus 1 tends to 0, where n is the Brunt-Weiss-Adler frequency. And so you derive them that way. On small scales, you eliminate all sound waves with an anelastic approximation, and that's a limit as the Mach number tends to 0. Now these are two quite different limits, and they don't mix very well. So you've seen lots of talks about, well, for instance, 2 weeks ago by Connor, trying to achieve both these limits in a single reduced equation set. And my feeling is that that's not been achieved in a satisfactory way. John Thuburn has been trying for a long time, for instance. My understanding is that you can't really do that, but in a sense, do you need to? So if you follow the approach the Met Office has been using for quite a long time, you solve the fully compressible equations, but you use semi-implicit methods to avoid the time step restriction, and that means you're not really computing sound waves at all, because the sort of sound waves you get will be nothing like real ones, because you've totally taken a huge courant number and the waves are going to be completely wrong. So the question, what are you doing? Well, you need to show that the method, because you want to use it operationally, will respect both those limits which you think do matter. Hydrostatic approximation is extremely accurate for large-scale flows, or well, in ECMWF, for instance, still use a hydrostatic model, and their forecasts are pretty good, so it can't be that bad. And on small scales, anelastic models are almost universally used for, say, studying convective situations, so that can't be too bad either. So we need, in an operational model, we want to use across all scales to respect both those limits. So I'm going to discuss the anelastic case a bit, really in connection with how the endgame integration scheme has been designed. So first of all, you can take a rather superficial scale analysis and say, oh, let's just go back to the equation. So in order to get rid of sound waves, all you really need to do is to get rid of this term. So in a rather superficial scale analysis, you just throw it away and you get that. And now you've obviously rather fundamentally changed the nature of the equations, because you've still got the right number of equations for the number of unknowns, but they're coupled together in a fairly unpleasant way. And it was learnt a long time ago, I think it was back in the 1950s, that if you just do that, you don't get equations that conserve energy, and therefore they probably can't be solved. So the idea was introduced way back on a small horizontal scale. You can just replace row with a reference profile, row naught, which is only a function of height. And if you're looking at only small horizontal and small vertical scales, you can just replace row by a constant. And the latter effectively brings you back to 3D or incompressible Euler equations, which you can probably solve if you add viscosity, if you believe that you can solve 3D incompressible Navier-Stokes. And even if you use this reference profile, you get a set of equations which are almost like a rescaled version of 3D incompressible Euler. So again, you would hope you could solve those equations. There's obviously been quite a lot of work since about more accurate ways of putting the reference profile in, and as far as I know, Gale-Durand's version is the best one around that still conserves energy. But now we're thinking of endgame, so we're thinking of discretization of the and we just think of the discretization of the continuity equation in endgame. So now Andrew Staniforth in particular wanted to make sure that there was no instability due to advection of density. So he wanted to use semi-Lagrangian advection of density. So we want that bit. And then you think, well, what you left with, and you're basically left with rho times div of u if you're discretizing the equations. And I've written, I'm thinking of a semi-implicit time integration. So this is rho at time t. Now, think about what happens to that sort of discretization as you take longer time steps. You're going to take a long time step for this compared with the Courant number. And because, obviously, this is just selection of a value of rho from a field that's sort of varying in a sensible way, taking a large time step means you're going to push yourself towards a solution with div u equals naught. So the limit of this will be something like the incompressible system, and that's only an accurate limit on small horizontal and small vertical scales, and it's not really what you want.
Are both rows multiplying by variance of u up t?
Yes.
And there is no default.
This is not the scheme they're actually using. This was just where its discussion started. I'm going through about 3 iterations of the scheme they're actually using. So don't worry, they're not trying to do it like that. I'm just trying to point out some of the lessons. That's the departure point. Right. Now, so definitely don't want to do that. So the next thing they did was to introduce a reference state, which is like that. And so now we have rho prime is semi-Lagrangian, and now we have the derivative of rho reference times u, and that's time averaged. And then you have to include, of course, you have to solve the right equation, so you need these terms as well. Otherwise, you'd be solving the wrong equation. And if the reference profile is accurate, this will converge to this solution, and that is obviously an anelastic solution. Might not be the most accurate anelastic solution, but at least you've now got something which is valid on large vertical scales. Now the issue with that was now, however, you can, because the solution of limit equations exists, you can now use that to test the model. In other words, you can take data, you might have a completely general density field, but it's not particularly close to reference profile. You can now take the limit as it goes close, as it approaches the reference profile, and see if the solutions converge, because you can create some artificial data to test your algorithm with to make sure it has the right limit. It doesn't have to be the same data as you're using all the rest of the time. So you can use that as a test, even if you don't think the reference profile will always be accurate. The problem with reference profiles, the solution won't be accurate on large horizontal scales where rho prime and rho ref are the same size. And Nigel et al. Found that, and therefore they modified the scheme again to instead use the value at the previous time step instead of the reference profile. So we get that scheme, which I hope I've written down correctly, is what's actually in endgame. And that means that it still has the correct small scale asymptotic limit, because then rho at time t will be like rho ref, so that if you really are in an anelastic situation where there's not a very big perturbation from a reference profile, you'll get the right answer. And now you want to get the large scales. You hope you're now going to get the large scales right as well, which is this limit, which requires this sort of cancellation after removal of a reference state with uniform theta. And as long as you've got removed this from the algorithm, you should get that right as well. And there's obviously that's what's been achieved. In their algorithm, there's no reference profile appearing, so that should be correct on large scales with no problem. And we're not aware of certainly the test with endgame suggests everything's fine. So, so this thinking is quite helpful in saying how do you discretize the continuity equation when they didn't want to use the new dynamic scheme, which clearly would have satisfied the anelastic limit because they were concerned about instability due to advection of density. And they sort of wanted to try to get both the advantages of semi-Lagrangian advection of density and the right limits at the same time. But this sort of argument shows that as long as you're a bit careful, you can do that. So we'll just summarise that bit. So we have to work on all scales in the operational models, but we can check separately that we get the anelastic limit right and the hydrostatic limit right within one scheme, and then we can expect the whole thing to work. And and these tests are quite important if we want to, let's say, build some other features in which may clash with, the new dynamics was designed to satisfy both those things, but then other issues came in like better stability properties, and Andrew Stanforth and Nigel Wood wanted to modify the scheme to make it more stable. So then you have to go through this thinking again and say, with the modified scheme, still going to get those limits right, because you can get some clashes between the two requirements. The other point is a bit more just to note that if you actually wanted to use the limit equation, this is a good example of a case where, which will stir it up a little bit at this point, actually using the limit equations directly is not necessarily a good thing, because you're really turning a weak constraint into a strong constraint. So, for instance, even the decentered semi-implicit scheme has a much, for the fully compressible equations, has a much lower condition number than the Poisson equation built into an elastic model, because you've got the correct sound speed rather than the sound speed set to infinity, and setting something to infinity doesn't do your condition number any good, so that it's actually much cheaper to solve a fully compressible model implicitly than the limit anelastic model. And then you can say, well, you almost twist the argument around by saying, supposing you were actually told you had to solve the anelastic model and it was really expensive, that using a semi-implicit Euler solver is actually a way of regularizing the problem in a physically correct way to make it cheaper to solve. So hope you've got the hang of that a bit. So the next topic is, this repeats a little bit of what I said 2 weeks ago, is the problem of frontal solutions. Now, here the limit solution is discontinuous because it's a semi-geostrophic solution, and this is quite, you'd expect this to be quite challenging for numerical methods, so therefore it's a good test problem. And you can think of lots of other test problems where they may be quite easy, but this one is quite hard. Let's talk about this one in a bit more depth than I did 2 weeks ago. So you create a clean test problem, because obviously we're going to use, the idea of this is you're always going to use a numerical method that you could use in the unified model, but you apply it to a simple test problem where you've got a computable limit, so you know what you're trying to do, what answer you're trying to get. But you're not allowed to specialize the method to the two-dimensional problem. So we use a dispersible cross-section, periodic boundary conditions in X, rigid upper and lower boundaries, and because we're using the Boussinesq equations rather than the fully compressible equations, these equations are actually a special case of solutions of three-dimensional equations, and they have good conservation properties. And one of the traps I fell into in working in this area, and so did Colin Cotter, was to do this with the compressible equations, because then the two-dimensional version of the compressible equations doesn't satisfy conservation properties and doesn't reproduce solutions of three-dimensional equations. When you run it for a period, you don't get the answers you expect. It's very difficult to understand why not until you realize you set up an inconsistent test problem. So you have to do this with Boussinesq. Now, the motivation is sort of indicated here. So here's a typical numerical solution for, let's say, using the Euler equations with sensible parameters. And you develop a very strong front at the upper and lower boundary, and you spin some gravity waves off from the front. This is a two-dimensional model, so gravity waves won't be like real atmosphere gravity waves, which a three-dimensional effect is pretty well always going to matter. And the issue is, as you take the limit, as the Rossby number tends to 0, do these gravity waves disappear at the right rate? Now, the really big incentive in this problem, the first incentive is to get this limit right and get the gravity waves to disappear at the right rate, and therefore represent a balanced state properly. But then the even stronger incentive in this problem is when you run this for a long time, you go through life cycles, and these sort of experiments have been published from time to time over the last 20 years. This is a plot of the radial kinetic energy against time, and this is a solution of the semi-geostrophic limit equations obtained by special methods which are genuinely conservative. These methods can't be applied to the full equations sensibly. So if you like, this is a reference, like an analytic solution, and you see this really nice life cycle that essentially conserving it. Solutions, these equations do conserve energy, and you just get this sort of life cycle, and that's sort of really appealing as a simple model of long-term evolution of weather systems, and you want to get through multiple life cycles of weather systems accurately. So you'd really like to reproduce that in the limit. Now this is a solution by Nakamura, 1994, and he was solving, in fact, this was still solving the semi-geostrophic equations, but using standard numerical methods of the sort you could put in a model. And essentially you can see the right answer was going to be there, but the whole thing is so diffused out, you nearly lose nearly all of it. You get a reasonable initial front, but the energy is way down, and after that you just get a little ghost of what you want to get. And really like to get a conventional numerical method which could keep a lot more of this energy and get a lot more of these life cycles. So there's quite a strong incentive to do better at this problem. So I'll just write up the equations. So those are the Euler equations of this geometry. And these two forcing terms on the right hand side are representing the driving gradients in the y direction, which never change in this problem. They just provide the source of potential energy to allow the baroclinic wave to grow and decay. And if you work out, these equations do conserve energy. And say about that. Now, to take the limit, small parameter, the Rossby number, and the semi-geostrophic limit, which is the appropriate reduced model in this geometry, obtained by neglecting these two acceleration terms, and it was also hydrostatic as well as semi-geostrophic, I should say, starting off with the non-hydrostatic Euler, and you get these as the limit equations. Now, this is where the theory is pretty solid that these limit equations can be solved, and solutions typically are discontinuous. That's been proved. Scale analysis shows that the solution is accurate to order epsilon squared, but the proof that there's the rigorous proof that tries to show that Euler does converge to this solution at required rate has not been fully achieved at the moment. It's only the proof only works to order epsilon. However, the computations suggest this result is true. It's a matter of this is where the mathematicians haven't been clever enough, probably. We'll see what happens. One of the nice things about using this as a test problem is that you can rescale it to let Rossby number tend to 0 without changing the semi-geostrophic solution. So in other words, the Euler solutions are converging, should be converging towards a fixed target. That's that's really good for numerical tests. It's not a very typical situation. Usually you have to show convergence towards a moving target. In this particular case, you don't have to. So this parameter beta rescales the length scale, velocity scale, and the Coriolis parameter, and that rescales the Rossby number same way. The other thing is, obviously nobody knows the answer to this, but the solutions of the Glucinski equations, most people will guess they probably stay smooth. Solutions of the SG definitely become discontinuous, so probably you have a case of smooth solutions converging to something discontinuous as epsilon tends to 0. That's obviously perfectly possible. very unlikely you get anything more than first order convergence because of the nature of a discontinuous solution. So you might sensibly expect order epsilon squared while it stays smooth, and probably only order epsilon once it's not. So let's see. And then I sort of mentioned this issue of the long-term life cycle of beads. PhD is basically to see if you can get close to this in a with a conventional numerical method. The two curves here, by the way, using this special method at two different resolutions, showing the solution is very robust to perturbations. It's not just a freak, it's very reproducible. So what have beads managed to do so far is demonstrate the correct limit using linearized equations, so there aren't any discontinuities. You'd expect second order convergence. And he's got 3 experiments. First of all, using a semi-implicit time integration of the linearized Euler equations with different amounts of decentering. So look at that one first. So here's the second order rates. Here's the controlling rescaling parameter beta. So you're looking at solutions that follow this slope. And what's happening is that if he uses Crank-Nicholson, so there is scheme of second order activity in time, the solutions don't hold on to the second order convergence rate once beta gets, so beta equals 1, which is here, is sort of, if you like, standard atmospheric parameters. You don't have to get much below that before you start losing the convergence rate significantly. But you just need to decenter with alpha equals 0.55 to start staying much closer. In all these plots down here, alpha equals 0.55 and alpha equals 1 give essentially the same answer. So a little bit, now whether that's needed in the nonlinear problem has to be found out. With the linear problem, it does need a little bit of help, with a little bit of damping to pick up the right convergence rate. This is just what happens as you increase the time step. And here they just seem to be a bit of an issue as you're really falling off the right convergence rate. But this is for this is just for the Crank-Nicholson centered integration. So if you did that with decentering, you'd probably still get the right convergence rate. Have you done that, Abid? Yeah. Do you get the right convergence rate? Yeah. So this would be true of anything other than Crank-Nicholson. And this is where you increase the resolution. This is still Crank-Nicholson, and the results are, you get somewhat better convergence with higher resolution. There's these circles at the highest resolution where you halve the horizontal and vertical grid lengths. So I have some nonlinear results soon. I showed some nonlinear results 2 weeks ago. They were from tests with the compressible model, not the incompressible model. They did show second order convergence through until the time of discontinuity, and then only first order convergence, and that was using the new dynamics scheme. So that looked as if the new dynamics was passing the test. Not aware of it, haven't been done with endgame yet. The problem with that setup is you can't continue past the front and get the life cycle because of the issues with the equations I mentioned. Right, so the next topic is work with Bob Beer, and what I'm trying to do is start filling in the gap between, so nearly all this sort of work has been done with adiabatic models, and really a lot of the interesting cases, physical forcing has a big effect. And for instance, if you do a dynamical core experiment without any friction at all, you get really silly answers. So people learned a long time ago, if you want to do a sensible dynamical core experiment to test a new model, you need to have simple friction in it. You can use something very simple, so it's not an issue what the formulation is, but if it's not there, you get stupid answers. So I was therefore quite motivated to try at least get into the boundary layer. Obviously just as important to get into the moisture, but this is just about boundary layers. And I'd really like to encourage people to do more of this, because these effects are huge. They're much bigger than the effects of whether things are geostrophic or not in terms of weather systems. Also, they're a pretty weak area of models, because everybody either works on dynamical cores or they work on very clever parameterization, and not many people work on how they fit together. So I really would like to encourage that. So, so here what we've done is I showed you a sort of shallow water version of this 2 weeks ago, where things are relatively trivial, but it was a good way of learning how things work. So here is what we're doing with a two-dimensional model. So that allows us to have a proper boundary layer scheme. Which is, so what I've written on the right is just looks like a standard vertical diffusion scheme. But what Bob is really putting into the model is a proper boundary layer scheme, which is actually much more non-linear than this, which correctly treats well mixed layers, for instance. I think the momentum scheme is more or less that. That's still fairly standard in operational models. So we have the thermodynamic equation with boundary layer term in it and friction in terms of the momentum equations. We're using the hydrostatic approximation, and we're using essentially Boossinesque, so it's incompressible. Key extra thing is because these terms are here, we now have a no-slip boundary condition, and that's quite important. What are the small parameters? Well, the Rossby number is going to be the ratio of the advective time scale to the Coriolis time scale. That's quite easy. And find an Ekman number, which is a ratio of a frictional time scale to the advective time scale. But this one is immediately starts getting difficult because Km is a function of the current state, and it actually depends very strongly on the velocity. And so the question is, can you really get the Ekman number? Can you really achieve a limit where this, as I've written it there, varies properly? That's one of the things we're not totally on top of yet. But it's obviously very important. If you want to be able to achieve frictionally dominated flows where, say, the friction balances the pressure gradient, it's very important in the tropics, but the convection is quite slow. And you've got to make sure you can actually mathematically write down that limit. So if you assume that, say, Rossby and Ekman both getting small, then the limit equations will be achieved by, go back a couple. So you get the usual thing is throw away the advection terms, and we're not making any assumption about this equation. You get Ekman balance from the momentum equations, everything else stays the same. Now that you can, by analogy with the planetary geostrophic equations, which are constructed like that for, well, without friction, we call this planetary geotriptic. Geotriptic is referring to, is a way of describing Ekman balance. That's if you hunt through the meteorological glossary, you find that term. So a way of getting to higher order would be actually to find the geotriptic wind by analogy with the geostrophic wind. So you do this, the UE, geotriptic wind. This has to satisfy the no-slip boundary condition in order for this to be solvable. And you then naturally go to second order by putting your advection inertia terms back in, but using UE instead of U. And that gives you something that's clearly consistent with the semi-geostrophic model outside the boundary layer, and you hope that will also work inside the boundary layer. So that's the obvious thing to make it second order. And now you hit one of these, you rewrite it like this, and now you hit a nasty trap because it's clearly the way to get second order accuracy, but if you look at this equation, I'm not going to go through all the derivation of this, is you've got due by dt, but you've actually got a minus ue over here, and so in a sense you've got, this term is not really going to work. Your kinetic energy is going to be replaced by the kinetic energy of the geotriptic wind, so it'll become like UE squared, and you could set this might do something unpleasant because this is a minus, and that's correct. If you actually work out the energy equation, you find the equations don't have a negative definite energy integral, which clearly they should have if they're representing friction, and that means the solutions will blow up. So, and you can actually make them blow up fairly easily. So that's suggesting that, well, certainly using this approach to getting second order accuracy, you can't achieve second order accuracy in a sustainable way. This method has been used for diagnostic studies where people have not attempted to integrate anything in time, they just diagnose boundary layer circulations by using this approximation, and that looks quite nice, but that approximation can't be sustained. So if you, say, ran a hydrostatic primitive equation model for some time and you find you weren't achieving Ekman balance to that degree of accuracy, and the reason you weren't is that it's just not sustainable because of this issue. You can achieve a second order accuracy if the Rossby number is much smaller than the Ekman number, so the rotation is dominating the friction, by reversing the sign of this term. Obviously this is still order epsilon, this term is UE is an order epsilon approximation to the wind, so this term is still small, but you obviously lose your second order accuracy, but by reversing the sign you now make the energy equation work, so now you have a sustainable approximation, but it's less accurate, and that's certainly going about things like this is looks like the best you can do. So we want to use that to test things out. And one of the results Bob has got he just created some data which looked like low-level jets, and he showed that it's well known that you get marked ageostrophic low-level jets, and there are various ways of getting these, but you can get them in storm systems where you feel they must be just associated with the balance associated with maintaining the geostrophic circulation, and this shows that there is the low-level meridional wind is quite a bit stronger when deduced from an SG type approximation with the boundary layer included than it is without, which suggests that you need quite a marked ageostrophic jet to maintain the geostrophic and Ekman circulations. That's a separate mechanism from the nocturnal jets that are often noticed, which are due to collapse of the boundary layer mixing when it gets dark. That's a completely different mechanism, which also happens quite a lot in this different situation. So that suggested we were doing something sensible. So we've got some diagnostic tests. So what we've done here is integrate the full equation for a period and calculate the momentum budget, and it allows us to check the scaling. Now I'm only going to show results for varying the Rossby number, not the Ekman number, because of not totally sure how to rescale it properly with Ekman number because of this dependence of the mixing coefficient on the velocity. So probably if you come to another talk in a couple of months' time, we'll have sorted that. But at the moment, just going to show varying Rossby number. So here's the X momentum budget. So this is the Rossby number is small and tending to 0 at this end, so everything coincides at 0. This is the Coriolis term, that's the friction term as written. This is written in a way that's sustainable, so this would only expect to give first order accuracy, and that's the thing you'd expect that's the property you'd expect to be maintainable, so it's the one you'd expect to be satisfied by the hydrostatic model, and that's the advection term, friction term. So out here, you more or less get the balancing friction on Coriolis directly. The advection term is not very significant at very small Rossby number. Rossby number gets less small, it's more a three-way balance, and roughly speaking, these three things add up. That's just a budget at one point, and here's a different point. And again, for a fairly large, for not that small Rossby number, the advection is a key part of the balance. You really do want to move beyond Ekman balance, because in fact these two terms actually end up both being the same sign, so you have to have this to hold it in balance. For a very small Rossby number, this term is negligible. So things are looking reasonable. We need to do more than this, obviously. So good balancing rotation, friction, a very small Rossby. So now we look at RMS errors. So for very small, so the RMS error in the Coriolis and friction are the red and the blue curves, and they're converging to 0. First of all, they're more or less the same as each other small Rossby number. This is where the advection term is getting much smaller. You can see that's dropping right down. And you'd expect this to be at least order epsilon, and it's not this. These dots are the first order convergence rate, and what seems to be happening from fairly small Rossby number down to here, you follow the reasonably close to first order convergence, which you'd expect, but then you seem to be losing it at even lower Rossby number, so that requires a bit of further investigation. It could be just the test procedure isn't really right yet, or it could be there's some issue with the model, we have to see, but that's something to study further. So just indicate that. And finally, now one of the issues with this model is that I'll take the point of the equations quickly. Right, so in these equations you've got total velocities implicit. You have an explicit evolution equation for the geotriptic wind, so it's like SG where the trajectory is determined implicitly, and that means you can't impose the no-slip boundary condition on U. You can only impose it on UE, but you know the true flow has to satisfy the no-slip boundary condition. So there's a potential issue with this setup not being able to satisfy the boundary conditions properly, and so we've checked on that in the numerical solution. What's happening here is that Rossby number tends to 0. Well, the wind speeds generally are going to tend to 0 with Rossby number, but what's happening is we're getting the difference between the total wind and the geotriptic wind is converging to 0 quadratically. You can see in this curve, which means that this error is order epsilon or order Rossby numbers you like. So when you multiply that by the fact the magnitude of the wind also decreases, you get quadratic, which is what we see there. So that aspect seems to be working okay. So we obviously want to study the convergence of the friction starts dominating. We're not quite there yet, so I haven't shown any of that because there's issues with the results. Okay, so I think that's all I want to say. So amazingly few interruptions. I hope it follows all. So that's it.
You mentioned essentially two approaches to solve the systems. Either you try to solve exactly the asymptotic limit system, like the analytic system, or you try to solve the full system, but you can't really do it, so you use time implicit methods. So you make, essentially you make a numerical approximation to the full system. But there may be a third solution, which is to, for example, a classic way of solving the incompressible Navier-Stokes equations, numerical methods, is to use things like artificial compressibility. So what you do there is that you change the speed of sound in the system, and you solve that exactly. So you make an approximation in the initial system and solve that as best as you can, which is sort of a third way in a sense, because you don't solve the right system, but you solve it properly, a bit like what you do for the analytic system.
Yeah, the question is that actually, do you actually end up doing anything different from the semi-implicit approximations, the full equations?
You do, in the sense that you control exactly how slow the sound waves are in the initial system. Because the problem with the semi-implicit discretization is that finding out exactly what the sound speed for each of the waves is very complex, and it depends on the detail of your method. It's going to depend on the amount of decentering, so it's actually a numerical you have numerical tunings which controls what you do in the end, which is quite different from changing the physical system and solving that exactly. So if you slow down the wave in the initial system, change the speed of sound, you will know what the speed of the wave is. You know it's the wrong one, but at least you know what it is even when you solve the system. It's a bit like solving the analytic system, where you push that to the limit and you say, you assume that the speed of the sound wave is infinite.
Yeah, I think that's not that. The way I would do that test, which I think is going to be almost the same as what you're saying. So you start off with your standard solution of Euler with the right speed of sound, and then to take the limit, you're just going to artificially increase the speed of sound towards infinity, and which I think is just what you're saying. And then you're going to say, as you increase the speed, as the Mach number tends to 0, you get the right limit, the right accuracy, and then you have the choice of either doing a plot with various different speeds of sound. Obviously, I was doing that in one of these problems where I would just rescale. I would never solve the limit equation. I would just rescale the Rossby number by some factor all the time, and just calculating the geostrophic residual, which should have converged to 0, and just showing it converged to 0 at the right rate. I'd never solve the limit equations, which are very difficult. So I think I was just doing what you said, just changing the parameters and comparing the solutions. And I can do that with the analytic case as well. You just change the speed of sound, let it tend to infinity, compute for a lot of finite values. But in that case, you can actually solve for speed of sound equal infinity by solving the inelastic system, and compare with that.
Sure. Yeah.
So I think what you're saying is more or less what I'm doing, because I'm artificially changing the parameters to converge towards the limit.
You would have to make sure that you're actually resolving the sound waves, compared to, so typically using an explicit technique with the CFL close to 1, so that you actually don't both slow down the waves in your initial system and also slow them down again by solving using semi-implicit technique.
Yeah, so that aspect will be a bit different, but yeah, okay. Well, it's obviously a good suggestion. Yeah.
I've heard you making those comments about the well conditioning of the resulting Helmholtz equation for a while.
Yes.
And actually, it really depends on how one designs the elliptic solver, because even if you take simple conjugate gradient, what it does, it really has a Helmholtz term, and it incorporates Helmholtz term and finds its coefficients variationally. So it changes from iteration to iteration. So one could say that if one uses those variational solvers, actually one goes through the sequence of different Helmholtz problems. And this is like, like with this artificial viscosities that keep decreasing to the inner limit to 0. So, and I did both. I solved both like a Helmholtz equation and Poisson equation for system representative of atmospheric applications. I didn't see any substantial difference, because the real physical constant is 1 over c squared. It's a very, very small number. It doesn't really improve much of the conditioning of the operator.
Well, if you're solving a sort of model on a quite large horizontal scale where there are other issues with it, of the reference state, then vertical preconditioning is very effective, whether it's Poisson or Helmholtz, and there wouldn't be such a big difference between them. If you run with I did these tests with aspect ratio, grid aspect ratio essentially 1, which is where you sort of ought to be using this model. And certainly, you see, I have to solve the Helmholtz equation for the compressible model once, and I've got the answer. But if I'm going to have to go through, if I'm going to use that as a way of getting the solution of the problem with C tending to infinity, so the inelastic limit, I've got to go through a sequence of values and take the limit. It's inherently more expensive because I've got to solve the Helmholtz equation several times.
Yeah, but this is. Are you thinking about direct solvers?
No, I always use iterative solvers. You usually use your iterative solvers. You use GCL most of the time. I haven't got code available. So, but I can't see a way where a problem with a higher condition number is not going to be more expensive to solve. However clever you are, because the condition number essentially is always going to determine how easy it is to solve.
Yeah, but actually, when you have a regular grid with this aspect ratio 1, then actually this reduces the condition number. Unless you are talking about having really large, very large, entire atmosphere done with a tiny resolution or direction.
Well, no, I was doing this for a test problem, so it was a limited area. So I had an grid aspect ratio of about 1, and I let the speed of sound tend to infinity and got the limits. I got a sequence of solutions from the compressible model, which converged quite reasonably to the solutions of the inelastic model. The inelastic model just solved directly. So I could have solved it by saying, well, I just take the limits of those other solutions, and you got almost the same answer, which I said, but having to go through that procedure adds cost. There's still more. Okay.
Looks like we have different experiences.
Okay, well, I've probably got as far as we can with that one at the moment. Any other questions?
So in the case where the PDE that you're solving, where you can prove it converges to the in the right asymptotic limit, that PDE converges to what you want it to, and then you do just a traditional, show that your numerical method is an accurate solution to that PDE, then don't you know, in that situation, your numerical discretization will also obey the same limiting behavior.
Well, what you're, which I'll quite unravel that, right? So you need to do this sensibly. You need to be using a numerical method that will get the limit equation right, because that's computable. So you should have used a numerical method that reasonably solves that equation.
Right, but I'm just saying, aren't there some cases where you can, if you just show that your numerical method solves the PDE that it's supposed to be solving accurately, then it must get that limit right.
Yes, if you solve that was the point, but then you're saying if you solve Navier-Stokes correctly, you'll get all the limits right. Yeah, I agree with that, but you just can't do that. You can't. This is to address the case because the solution of Navier-Stokes is not computable. So you can't. So what your operation model is never going to solve Navier-Stokes correctly because the resolution is way off what you need. So, for instance, you start producing a mixture of things you resolve well and things you don't resolve well, and are you?
No, I mean, though, let's take the example if you're solving the non-hydrostatic
Yeah.
equations very accurately, then you want to show in the hydrostatic limit.
Yeah.
So if your equations converge in that limit.
Yeah. Well, if you actually solve the non-hydrostatic equations correctly, they should have the right hydrostatic limit, because theory, the numerical errors are not significant, and the analytic theory tells you get the limit right. So the point of doing this exercise is a situation where you can't solve the full equation correctly. Because even in some of these simple setups, the solution of 3D Euler will still be lots of 3D turbulence, and you never, at least 4 degree, you never know if you've got it right. So the idea is to deal with a situation where you cannot solve the full equations correctly. If you could, you wouldn't bother, you just solve them.
Well, should we call it a day there, and there's time for discussion tomorrow afternoon?
I encourage people to think of items, either different problems you can do like this, or useful problems you can do like this, or other ways of doing the experiments, and come back tomorrow and throw them up. I shall work out a few things to get the discussion started with, but hopefully you'll come back with lots of input.
Thanks again tonight.